Okay, so how is everyone today? Good, I hope? All right, so then some of you have had your problem section between last time and this time, the first one, which met on Tuesdays, and then some of you are going to meet for the first time on Thursday. Great. I posted a video to YouTube. Did y'all get that message? Yeah. Okay, good. And then I haven't set up the thing where you can download the notes, but I will. Good. Any questions before we get back to math? Yeah. Yeah. I'm sorry. I believe that's right, but the problem section meets this week. Good. Good. So last time we were talking about we had ended talking about distance. So here we are. So this is distance, and to be clear, when I say distance, I mean unsigned distance, which means that that's like the way folks usually reckon distance. So if the distance from like Dallas to Houston is 200 miles, then the distance from Houston to Dallas is also 200 miles, right? Not negative 200 miles. Okay, so in the reals, that is to say, just on the line. What we're interested in is the length, the distance between 2 points, not vectors, but 2 points. So if this is like point A there, and this is point B, then what we want is to get out a ruler and measure that. Okay. So what's the formula for the distance? Okay, good. Good. So then, you can write it like this. You can say something like this: the distance from A to B is B minus A. And as for the picture that I wrote, what I've currently written is correct. But if I were to modify the picture so that the green point was to the left of the red point, then I would no longer be correct. So how do I fix it? Very good. Well, I have to write absolute value is what fixes it. But I want to be clear about something, and that is that I want you to think of this in the following way. A minus B, and then this is equal to, and we're going to do it like this. We're going to say that first thing is we're going to take that A minus B. It doesn't matter, A minus B, B minus A doesn't matter. So we're going to take that A minus B and we're going to square it. So that surely can't be right yet, okay? If I were to stop here, because surely you don't square things and just leave it to find the distance. Then you follow this up by square root. Now, here's the deal, is that I asked y'all, I think, to consider the following expression. So the square root of x squared like this. Is this equal to x for all x? No, it's not. It's not. So let's be clear about it. There's two processes that are occurring to that x. Okay, there's the squaring one and there's the square root one. Now, which one occurs first? The squaring, and then that's followed up by square root. Okay, so let's consider that carefully. So how about we take a 3 and then we square it. So to remind you, usually when you write an exponent, you don't write any punctuation like a plus or anything. You just write it as in the superscript position. But the punctuation for it is this caret. So we're going to take the 3 and then we square it, and then what do we get? 9. Incredible. And then we take that 9 and we give it to the square root machine, and then what comes out? 3. A 3. Okay, so far so far it kind of seems as if that this really should be true. But let's consider, how about this one? -4, and then now you visit the squaring machine first. So you square the -4 and you obtain what?
Positive 16.
You obtain 16, and then you take that 16 and now you give it to the square root machine, and what comes out?
Positive
4.
4.
So do you observe that the process began with -4, but out came positive 4? Okay, so as a result, this is false. Okay, nevertheless, I've taught calculus lots of times, and students seem to overlook this a lot. So the square root of x squared is in fact the absolute value of x. Good. Fine. So then now 2. So this is distance in the line, on the real line. Now we want to consider the distance on the plane. Okay. So as for the plane, we could draw it like this. So now we've got a red point here. I'll say that that's point, say, A1, A2. Because remember, now that we're on the plane, we need two numbers to specify the name of a point. And then we've got some other one here, B1, B2. And then what we desire is we desire the length of this graphite line segment I just drew. Now here's the deal. You've got to understand the rules that are at play, is that we've got 2 copies of the reals, the horizontal copy and the vertical copy. And we've got a ruler, you know, like a linear measuring device. And it's completely fine for us to use our horizontal ruler and measure stuff horizontally. It's completely fine for us to use our vertical ruler and measure things vertically, but it is absolutely forbidden on pain of death to turn that ruler at an angle. Now, I'm not saying that those are reasonable rules. I'm just saying those are the rules. So the way that you make this work out is you say, okay, well, I'll project these down to this axis. And what's that point on the horizontal axis? A1. And then this one is B1. Similarly, Gesundheit. Similarly, projecting these over here, this would be A2 and B2. And now, here's the thing: is that now that we have 2 one-dimensional problems, we can measure the distances, right? Because we just talked about that up here. So as a result, you can tell me what's this distance right here? Almost. Absolute value. So this would be this one right here is absolute value of B1 minus A1, or A1 minus B1. Obviously, it doesn't matter. Okay. And similarly, what's this distance here?
Absolute value A2 minus B2.
Okay, good. I'm going to write it with the B's first, because I don't care which one you do it, but it kind of you know, gives me an itch if I don't do them both the same way. All right. Now here's the thing, is that R2 is a rectangular coordinate system, which means that all these lines are parallel to each other, which means that not only is this distance absolute value of B1 minus A1, but so is that one, and similarly that one, and this is not just any old angle, that's a right angle, which means that, you know, what that's telling us is that we've got a right triangle, okay, and we know the length of the legs, which is to say the sides that aren't the hypotenuse. Okay, Pythagorean theorem, right? So that means that this distance here, d, you could write it as d squared, is b1 minus a1 squared like that, and then plus b2 minus a2 squared like that. Okay, now I wrote those as absolute value. Now I'm going to write something, and I want you to just quickly remind me why it's okay for me to do it. So, right, so then, if b1 minus a1 were negative, then the absolute value would switch it to positive, and then we'd square it, and then it would be positive. Whereas what we're saying here is that, well, let's just omit that whole absolute value bit because we're going to square it anyway. As a result, now we can solve for d and get that d is the square root of all this business. Okay? So now, in case it wasn't clear, the reason why I insisted that we're going to write distance like this on the line, the reason why we're going to write distance like this on the line is so that it looks like this, as it is on the plane, right? So, as a result, the way that we're going to write this now, just as a matter of notation, is we're going to say that the distance from A1, A2 to B1, B2, like so. So 2 points, and then subtracting them, and then putting them inside vertical bars. So now, strictly speaking, this is not absolute value because absolute value is only defined for real numbers, right? But this couldn't possibly be a real number. So what I'm saying is that but when we write this, this is what is meant. So this is a definition. All right, good. Any question about this? So now here's the fun thing, is that what I want you to observe is that in R1, what you do is you perform a subtraction on a line. Okay, you square the subtraction that you made, and then you compute the square root of that. In R2, you perform 2 subtractions on 2 different lines. You square each one of them, you add them, then you compute the square root of all of that. That's what you do in R2. What do you think we're going to do in R3? Right. It's exactly the same problem, okay, reducing it to 3 one-dimensional problems, right? This is a one-dimensional problem. We recognize this as 2 one-dimensional problems. And the last one is 3 one-dimensional problems. Okay, so let's write that down. But now it requires a little bit of artistry to make it work visually, anyway. So here we have, you know, a 3-dimensional axis, and remember we have to look at it in perspective. And this will be a good time for me to ask again. Okay, so in the standard convention for drawing 3-dimensional axes, which one is which now?
Bottom line.
Okay, this one.
Yeah.
Okay, what is this one?
X.
X, okay, and this one?
Y.
Okay, and this one? Z, good. So that's the right-handed convention, okay? The way you can tell you have it right is that if you put your thumb in the same direction as Z, Z is going with the page, so up that way, then your fingers should curl, okay, from your right-handed fingers, should curl from X to Y. Okay? So if it were the other way around, you know, you couldn't make it work. By the way, if you take organic chemistry, it's so funny because, like, you know, this is a big part of it. It's a big part of it. You know, you got to look at a carbon molecule, well, a molecule that contains a carbon atom, and if it has 4 different kinds of bonds, then, you know, you got to figure out, is it a more or less a left-handed bond or a right-handed bond? And you know, and you look at an OChem exam, you'll see like everyone going, you know, trying to, like, you know. Anyway, it's pretty funny. But, you know, there's interesting stuff about it because, you know, for example, I don't know if I said this, but you know, if you take the molecule that has lemon smell, then its reflection is what smell? Pine. And there's a lot of like cute little examples like that, but some of them are kind of deadly actually, and they cause diseases, so they're not so cute. All right. That being said, so now we've got some point here out in 3 space. So A1, A2, A3. Okay, so then now, you know, the trick to making this work, to making this seem sensible in a picture, is that you say, okay, well, I'm gonna go from here, and I'm gonna go down to the XY plane there, and then you just stop, you know, just anywhere that seems reasonable, like right there. Okay, so right there is where I'm gonna stop. So now, to find out where that point goes, you turn this axis towards you, and now draw the dashed line to the Y, parallel to it. So right there. Okay, and then here like this. So that means that on the XY plane, this point right here would be what? A1, A2, right? Which means that on the x-axis, what is that? Whoops. Sorry. My hand was resting on the zoom button, apparently. Oh, come on. Every time you zoom it, it wants to adjust the lens. Okay, there we go. So this is what? That's A1, right? And this one? A2. So right there. You know, and then, let's see, can I remember how to make it look good? So then I can, yeah, like this. So then I come up this much, that much, that much. So that must be A3. Right, so now we've kind of located that point in space. Okay, you saw me do that, and I'm not going to do it again. Okay, because, you know, I'm also videoing it. So now just imagine that there's another one. Okay, right there. B1, B2, B3. Okay, and then, you know, I could carefully locate it in 3 space. Okay, fine. Then between those 2 points, we can draw a line segment, like so. And the request is to find the length of that line segment, so that everybody understands the question, right? It's exactly the same thing, okay, as before, except instead of there being 2 one-dimensional problems, now there's 3 one-dimensional problems. The length of that, so A1, A2, A3, B1, B2, B3. So the distance from between those 2 points is what? Does anyone care to speculate?
Square root of B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared.
Very good. Whoops. B1, A1, B2, A2, B3, A3. So all that means is that that's the length squared along the first axis, plus the length squared along the second axis, plus the length squared along the third axis, and then square root all of that. Okay, that's why the 1's go together, the 2's go together, and the 3's go together, because it's first axis, second axis, third axis. And then, you know, I don't need to explain anymore. You know, even if there were like 1,000,000 axes, as painful as the arithmetic would be, in principle, you could now do it. Okay. Any question about this? All right. So now, that being said, now I can remind you of some interesting stuff. Is that I'll leave a 1 here, and I'll come back to that in just a second. And I'm going to start here and write R2. And now I want to say, suppose that we have a point. So given a point hk in R2 in like this R2, the set of all points of distance r greater than 0 from so that what I mean by r greater than 0 is that's some fixed constant. So this is fixed and constant from hk. Well, that's an interesting set of points. Interesting enough to maybe have a name. What's the name? If you draw a plane and then put a point, and then say I want to know all the points that are, for example, distance 8 from this point. You know, so you could like go up and find a point, some other point that's distance is 8. You could go down. You could go left and right. You could go at a pretty much any old angle. What's the name of that? Circle, right? It's a circle. So this is called a circle. You know, and you can be, you know, really precise with the language and say, well, it's the circle of radius r centered at hk. Yes? This? That's an r. So writing it really big, you know, like this. So the convention that I use is that when I'm writing prose, like a language, I write it in block print, and then when I'm writing math symbols, I write them in script. All right. So then the formula for this is going to be, well, it's going to be this, right? It's going to be the set of all points x, y, which satisfy this equation. So the distance, so that's the distance from xy, from a point xy to the fixed point hk, and we're saying that these are supposed to be equal to r, right? But you know, in fact, we've got, you know, you've seen the equation of a circle before, and it probably didn't look exactly like this, right? So let's work it out and make it look good. So in the first place, we can replace this with that square root thing on the previous page, so that it looks like this. So square root of what have you. So what do I put in there? X minus h, because that's the distance along the x-axis, right? Along the first axis. So x minus h, we got to square that, and then plus what? Y minus k, square that. And then even this is not the usual way you write a circle, the equation for a circle, right? Usually you do what? Usually you write it without a radical, you know? You write it over here. So, oops, x minus h squared plus y minus k squared is r squared. So this is the standard equation of a circle centered at hk with radius r. Okay. Any questions about this one? Okay, so then visually, you know, it looks like this. So here's some point, hk. Oh, you know what? I broke the rule of drawing a circle. The rule of drawing a circle is you always draw the circle first, and then you draw the center next. Because it's actually quite difficult, in my experience, to draw a circle around a point. But here I go. And that's my best effort. So all such points, x, y, on the circle, what we're saying is that this length has to be r. Okay, good. So now, let's do an exercise. So any question about the statement? Okay, good. So now I've got to remind you of some boring algebraic details, but nevertheless, you know, this is stuff you have to know. All right. So now I'm going to write a little block, but instead of calling it an example block or a remark block, I'm going to call it a hidden block. So this is something I'm going to write, but this would be like something that I write in my office, you know, and then I don't show you. All right. So then if I wanted a circle centered at, say, at the point 3, -4. Suppose I want a circle at that point. So if I want this to be the center, and then you know, then I choose the radius to be something like I don't know, 9. Choose the radius to be 9. Then the standard form for a circle looks like this. I would write x minus 3, square that, and then plus what? Y plus 4. Again, the plus now, because that's a -4, is 9 squared. So now I'm gonna multiply this all out, and I'm gonna say that this is what? This is x squared minus 6x plus 9, and then plus y squared plus 8y plus 16 is equal to 81, like this. And then now I'm going to collect all the constants together. So that'd be 25, and then 25 minus 81 is what? I have no idea. -56. So here's the question. Suppose I say, you know, I say let x squared minus 6x plus y squared plus 8y minus 56 equal to 0 be a circle. Okay, that's the equation for a circle. What you need to do is you need to find the center, radius, and standard form equation. Now, it's a little bit disturbing, you know, that literally the answer is right there. Okay, but understand that when you're faced with such an exercise, it's not going to be there. Okay, so the question is you saw me do this. You saw me do it. Essentially, what I'm telling you now is that you've got to know how to undo it. So what's the name of the procedure for undoing that? Starts with a C. Complete the square. We got to complete the square. Not just once, as fun as that would be. We're going to do it twice, once for each variable. Okay? So we must complete the square for x and for y. Okay. So to remind you of this lovely thing, the way it works is that you group all the stuff with x's together. So these terms have x's, and they're going to have a party. So I'm going to leave. I'm going to give them a big house there, and then now we're going to group all the y's together, y squared, and then plus 8y. They're having their own party, and then I'll leave the constants out. They're not invited. So now, within the parentheses, the extra room, okay, we need to carry out the complete the square procedure. It amounts to a neat kind of trick. So it works like this. So x squared minus 6x. I'm just copying the line above. And inside of those square parentheses, I'm going to add 0, because 0 is the only thing you can put in there that doesn't actually alter the equation, right? But the way we're going to do it is we're going to actually add a thing and then subtract the same thing. That's the way we're going to do it. So if we were to add 8, we'd also subtract 8. So specifically what we're going to do is we're going to add something and then subtract the same something. And it's going to be something divided by 2. So we're going to do that both times. We're going to divide something over 2, blah, blah. We're going to square it. And the one piece of information that you need to know to finish it off is that what is it that we put in that numerator? Not 12. Negative 6. You take this coefficient and you put it there and there. So negative 6 in here, negative 6 in here. All right, so negative 6 over 2 is negative 3. You square that, what do you get? You get 9. So this would be x squared minus 6x plus 9, subtract 9. Good? And then plus, now what are we going to add and subtract in here? 8 over 2, all squared, right? So it'll be plus something over 2 squared minus other something, same something, over 2 squared. And the thing that goes in the numerator there is this coefficient. And then when you get accustomed to this, you realize that the sign of that coefficient doesn't matter because you're squaring it. So 8 over 2 is 4, squared is 16. So then we have y squared plus 8y plus 16 minus 16 minus 56 equals 0. Now here's the deal. The reason why we did this is that in each group, the x group and the y group, notice that these first three terms are a perfect square, which means that these first 3 terms can be written as something squared. X minus 3 all squared. So this is x minus 3 squared. I'll leave that subtract 9 there. And then plus. Now, these first 3 terms can be written as a square. What square? Y plus 4 squared. And then I'll leave that 16 there. And then subtract 56 equals 0. Now I'll collect all the constants and put them on the right-hand side. What constant goes on the right-hand side then? 81. So x minus 3 squared plus y plus 4 squared is equal to 81. But of course, 81 is 9 squared, right? So as a result, now we can read off the answer. What is the center of this circle? Three, negative 4. What's the radius? 9. And the equation, therefore, is x minus 3 squared plus y plus 4 squared is 9 squared. Okay? So now, what I want you to understand is that really the carrying out of this problem is really 2 simultaneous problems. It was this problem in the left column and that problem in the right column, and they were completely separate until the end when we needed to combine them. Okay? I'm not gonna do it, but I'll just say that there's a corresponding 3-dimensional problem, right? What I mean is that I wrote x's and some y's and a constant. You can imagine doing exactly the same thing with x's, y's, and z's, right? Or x's, y's, and z's and w's. Okay? Then you'd have to complete, in that case, 4 squares. Enjoyable. But understand that that's what's requested and required. Any questions so far? No question? Yeah? Yes?
So we're going to have to do this in 3-dimensional.
Right. Correct. It'll be just like that, and the question will be, find the center and the radius, but it won't be find the center and the radius of a circle. What will it be? Sphere, right? Because the corresponding question is that if you have a point in 3 space now, and you want to consider the collection of all points that are, say, distance 3 from this point right here. Well, the name of that collection of points is so significant it has a name, and its name is sphere. So in that case, you'd want to find the standard form equation of a sphere. And from a question, if the question is phrased like this, then where computation is concerned, it's just like this one, but instead of 2 subproblems, there's 3. Okay, good. Any questions about that? Other questions? All right. So I'll continue that remark that was on the previous page. So in the case of R3, the book writes, okay, HKL. So the set of all points of distance are positive, fixed, from point HKL Okay, so now we've got some HKL point just sitting there in 3 space. And we want to know the set of all points that are distance r. All right. So so this is called a sphere. It has equation xyz, distance from xyz to HKL is r. But in the same kind of way that this is not the manner in which you usually write the equation, we could go to radicals, okay, and then we could move the radical to the other side and make it as a square. I'll elide all of that. You can fill in the details. It would look like x minus h square that plus y minus k square that plus z minus l L square that is equal to r squared. Okay. Any question about these definitions? All right. Now I have a question. Kind of got to think about it. In R3, so in R3 now, what is the set x squared plus y squared is equal to 4? That is to say, what is the set of all x, y that satisfies this equation? What does it look like? Well, let's think about it for a moment. Notice that I said in R3. And that's not a mistake, I meant that. But kind of the way the equation is written, it kind of lends itself to kind of thinking about it in R2, right? Let's substitute R3 for R2 momentarily, and I'll ask, well, what would it be? What would it be if it was R2? What would this be? Circle of radius 2, centered at the origin, right? That's what it would be. So if it were it's not, but if it were R2, then we'd be looking at something that looks like this. Okay, that's what it would look like. This would be this is x and this is y. Okay, but we're not talking about that. We're talking about R3. So while it's dawning on y'all, I'm going to draw a picture and say, well, in R3, it would look like this. So what I'm going to do is I'm going to take this picture. I'm going to take this picture and I'm going to give it a twist, and I'm going to draw it in the XY plane, but in the XYZ axes. So now this is z, this is x, and this is y. Okay, so then it's like I'm going to take this picture and I'm going to turn it and lay it down in perspective. So here is you know, 2 in the x direction, negative 2 in the x direction, 2 in the y direction, negative 2 in the y direction. So we would have this, you know, this circle down here in the xy plane. And that's the best I can do. Not really an artist. All right. Now, is this the answer to the question?
No.
No, it's not, right? So in particular, this particular circle that I drew it on the xy plane, which means that it exists at what z?
0.
That's for z is 0. But notice that the equation doesn't mention z at all. So this is part of the answer. It's the part of the answer when z happens to be 0. What about when z is like, you know, like 8?
Still correct.
Yeah, it'd still be just as correct, just as true at 8. And what that would be is that I take this and just move it up here at height 8.
So would that mean that this circle would technically be everywhere
At all z levels. So in fact, what kind of thing are we talking about?
It's a long cylinder.
Yeah, a cylinder that goes all the way up and down, right? So it's like this. You know, it goes all the way up, you know, and also down. And you know, like so. All the way up and down. Neat. Okay. Any question about it? So you know, you could make different arrangements to where instead of the cylinder being like that, you could, you know, turn it so it's like that, you know, like this, going that way, or whatever way you care to make it. Any question about this? All right. How about this one? You know, just describe generally. How about something like x squared plus y squared plus z squared is less or equal to like I don't know, like 25. So what would this be? So now I'm really mixing it up, right? Instead of equality, now we have inequality.
The filled sphere, radius to 5.
Right. So now understand that when a mathematician says sphere, they always mean just the shell. Okay, not the contents. Okay. So when you want to describe what this is saying, what this means if it were exactly equal, then the answer would be that this is the sphere of radius 5 centered at the origin, if it were equal. But because it says less or equal, that means that in fact all points inside of that sphere are also included. Such an object is called a solid sphere. Okay, so this is the solid sphere. Of radius 5. Centered at the origin. Okay, neat. So another fun game to play would, you know, could be something like this. How about 3 less than x minus 4 squared plus y minus 24 squared plus z minus 14 squared less than, I don't know, 10. So now what is this? Sorry? Okay, good. So in the first place, just that bit by itself, you know, ignoring the inequalities on either side, you know, that's looking like one side of the sphere centered at 4, 24, 14. Right? Now, if it were just this, we'd be talking about the interior of the solid sphere, but not including the boundary of radius what? No? No?
Oh, no.
Square root of 10, right? radius square root of 10. So you got to be careful about that one, you know. And this one, if it were by itself, it would be, you know, everything that's outside of the corresponding sphere with radius square root of 3. And then this is, you know, something like a, you know, I like the description, a thick shell, a thick sphere, you know. It's the set of all points centered at 4, 24, 14, but it's like you deleted out the little bitty sphere in the middle. You know, kind of like, you know how the Earth is, you know, more or less a sphere and it's got that core in the middle. You know, if you could just like delete it, and then there's nothing there. That's the kind of thing we're talking about. Any question about this? Doing good. So now we're going to talk about vectors, and then we can get back to calculus. All right. So we mentioned points, the distinction between points and vectors on Monday. Remember, points are specific positions in either the line or the plane or 3 space. Like you could single one out. That's it. Okay, and you draw it as a point. Whereas a vector is like an arrow with a tail and a head, and it's not located at any particular place. Okay, so you can take a vector and then rigidly move it to another place without twisting it or turning it, and it's the same vector. Okay, so in the 2 minutes remaining, we're going to talk about vectors. So specifically, we're going to talk about adding them first. So they have a nice visualization. So we could say, what if we have a vector u that I'll draw like this. So u is this vector. So when you draw a vector, you've got a letter, and then to signify that you know, it's something special, like maybe not a real number, you give it a fancy party hat, and it looks like this. So it's a hat, and that's a little arrow, but it's that's called a hook, because it's not a double-sided arrow. It's just got a little hook on it like that. And then so that's u, and then if we had some other vector, like you know, say like maybe like this, v. The question would be, is that how can we add these together? We want to add them, you know. So the way you add them is that you choose either one, okay? But because u's on the left, I'll choose it. Now I'll make a copy of u. Now understand that this is exactly the same as u, because it doesn't matter where u is located. That's not relevant to the identity of a vector. And then what I'll do is I'll take v, and I'm going to arrange matters so that the tail of v is at the head of u, which is to say like this. Okay, so it doesn't matter that I moved u and v around. The only thing that matters is that I didn't twist or turn them as I did it. So then, what's the answer to the sum then? How do you figure it out? You start at the tail of u. Tail of u to the head of v. You know, which is to say, this is the tail of u, that's the head of v. So this is u plus v. Interesting. Interesting. So I know that many of you have seen this kind of thing before, but my experience tells me that it's been pretty superficial. So the thing that we're going to start with next time is that not only we're going to add vectors with this head-to-tail business, we're also going to subtract them. So the subtraction of vectors in this way, you know, if you thought this was, yeah, I've seen and heard this before, with high probability, I think that you will not know exactly what to do when we're talking about subtracting them. But we'll talk about it on Friday. So have a nice Wednesday.